All right, guys, hello to everybody. Mr. Jones here. This is actually the last video I'm filming for the Unity Read crew here. So, Algebra 2, hello everybody. We are just going to go through this topic of graphing polynomials, and this will be interesting because I can't actually edit this video like I do the other one. So if I burp or something or somebody interrupts, then it'll just be in here. So let's see how this goes. Okay, so yeah, so we're talking about graphing polynomials here, okay? And this will be the first video that you guys see in the polynomials unit, okay? So just defining what is a polynomial, just breaking down this word. I define it as a group of multiple terms, okay? So just, you know, I like to say things in terms of groups, so that would be, you know, like an example of a polynomial, you can have a small polynomial, 2x minus 5. That's a group of multiple terms. You could also have like 2x to the fourth minus 4x to the third plus x squared minus x plus 10 or something like that. Right, that's a huge polynomial, but yeah, so that's just a polynomial just means a group of multiple terms of any size or type, okay? So standard form of a polynomial would be like I have it here, just kind of just a group of terms listed out like that. Okay, so that would be a polynomial in its standard form just by itself, but as a function, right? A function means it's kind of an equation sort of thing. So you could say at the beginning here, y equals that. That would be an example of a standard form polynomial. And that's opposed to factored form. Factored form means it's in those individual groups kind of broken up. Okay, and we'll talk about that later in the unit. Okay. So that's just the basics. Okay, the degree of a polynomial. It's kind of right with these big groups. We can name them a couple of different ways. So the degree of a polynomial, like the one above, I would call that a fourth degree polynomial. That just has to do with whatever the highest exponent is. Okay. So fourth degree. If this was a 5, it'd be a fifth degree. We know that if it's a 3 or a 2 as the highest exponent, those have special names. If the highest exponent's a 3, we call it a cubic function, and then if it's squared, we'd call it a quadratic, or if it's 1, it would be linear, right? But then after that, we just start going fourth degree, fifth degree, and like that sort of thing, okay? And then in terms of the number of terms, right, we have a binomial or a trinomial with 2 or 3 terms. And then after that, you could say with 4 terms, with 5 terms, whatever. So just basically, that's just saying there's lots of different ways we can name these polynomials based on how many terms there are and what their highest exponent is. Okay. There's a couple of things in here I'm not going to go over just for time and brevity. So just going over what these things are, local and maxima and local minima. Okay, so let me just give you an example of a graph here. So y equals x to the 4th power. Okay. So we see this graph, and it's going to show up like this. Let me actually change this a little bit. Y equals x to the 4th plus 3x to the 3rd. Let me make it look something like this. Okay. Okay, so we see this graph, right? And obviously, the more complex the polynomial and the bigger the exponents, the more complex the graph, right? So and that makes sense. Let me just add a couple more things in here. That does not look how I want it to look, so hold on. I want that. Hold on. There we go. Okay, now that's looking a little bit better. Okay, so the characteristic, and that's dropping way down low there, but the characteristic of this graph, okay, is it's going to have the more, the higher the exponent is, the more turning points we would call those are, okay? And what those turning points produce are these local maxima and local minima, okay? So basically there's just all these different curves with all these different complex graphs. And so local maxima and minima are basically just these high and low points on each curve, okay? So Obviously, the high points would be called maxima and the low points would be called minima, okay? So when we look at the graph, okay, we have, and that local means like it's not the highest or lowest point that it ever touches. It might be, but it's just on each specific curve, okay? So like this point right here, negative 0.545, negative 2.211. That would be a local minima, okay? That's a point on a curve where it's low and then it turns from there. So it'll be called a turning point, but it'll also be called a minima, okay? And then it comes up. It highlights the intersection points here where it crosses the x-axis, but we're not concerned with that. You see the next point, right? Let me zoom in a little bit. It comes up here, right? And this would be a local maxima, okay? 0.622 in this case. So that would be a local maxima, the highest point on a curve, the point where it starts to turn down. And what's really nice is Desmos highlights these for you. Okay, so that's what I would recommend. Continue to use Desmos. And then again, I showed the whole graph before. We have a local minima all the way down here at 4, negative 109. So that would be obviously a local minima too. And that would be the lowest it ever touches. And that lowest point ever, if you were asked for the domain and range, that would be important for the range as well. Okay. So there we go. Okay, so just a couple more things to go over before we talk about some specific things. Okay, so ending behavior. Okay, so ending behavior. We're more concerned with like, so you're gonna have a small little mini table here, left and right. Okay, so on the left of the graph, like as the graph extends to the left, you're wondering, okay, is that gonna, it's either one of two options. It's either gonna go up forever to positive infinity, or it's gonna go down forever to negative infinity. Okay, so in this case, with the x to the 4th graph, we see that it on the left of the graph, right after all these curves, it's going up forever, right? So we would say for this one that it goes to positive infinity, okay? In the right of the graph, right, it dips all the way down and then starts to come back up, right? And then it goes up forever. So that would also be positive infinity. Okay, it's going up to positive infinity. If it was going down forever, you could say negative infinity, right? You could also put arrows, right, like going up forever, going up forever. And if it was going down, you would say down forever, but yeah. Okay, and then intervals for increasing and decreasing. This can be tricky, okay? This can be tricky, and I'll actually have to pull up another picture here to highlight that. So I'll do that here in a second, but we'll just, that is something that is gonna be a tricky one to explain with Desmos. But okay, so just talking about these parts of the graph and these different new vocabulary terms, that's what we have, okay. I'm not gonna go over this, just writing a polynomial in standard form. Basically, the only thing with these is that you want to, like, you would combine your like terms in this case, but you're in polynomials, right? The standard form is highest to lowest exponent order. That's the order that you want to put these terms in, highest to lowest exponent order. Okay, so in this case, we would, combine the like terms that we can. And then like the highest exponent in this group would be a 4, so that term would go first. And then x squares, that would go second, and after that. Okay, so that's similar to stuff you would have done in Algebra 1, but more concerned with the graphs here today. All right, guys, so it's just asking us 2 questions here, and I think that's all we're going to look at here because we've talked about this factored form and stuff in other videos. So, okay, just talking about these 2 graphs and talking about their shape and their general details, and you can sketch a graph as well. Okay, so let me put number 3 up there. And I know it says f of x because that's our function notation, but again, we said before too that f of x and y can mean the same thing, right? We talked about that with our composite functions. So x cubed plus 3x squared minus 4. Okay, so we see this x cubed graph. And we talked about cubic graphs related to transformations, right? But we didn't look at too complex of cubic graphs. Okay, so now this one, it comes up from the bottom, comes up, dips down once, and then starts going up again. Okay, so we see there's one less turning point on this one, right? Because there's the exponent is one lower, right? So that number of turning points depends on what this degree or highest thing is. Okay, so you might be asked about all these different things. Okay, and I will pull up a picture or an image of what this increasing, decreasing intervals is. Okay, so let's just talk about all these different things related to this graph, and then we'll do another one, and then we'll be all good. Okay, so the shape of the graph, again, the shape is just like the general like parent function type thing. of what generally x cubed graph looks like, okay? So when we look at this one, okay, an x cubed graph generally starts down low here, comes up, dips down once, and then starts going up again. Okay, so that's what an x cubed graph generally looks like. Okay. In the ending behavior, okay, so again, this is where we make our little mini table, and we're talking like, okay, on the left of the graph and on the right of the graph, what direction is it going in? Again, we'd say on the left it's going down forever, or we could say that's going to negative infinity, and then to the right it's going up forever, right, or towards positive infinity. Again, we can just see that by observing the graph, right? As it extends to the left, it's going down forever, and as it extends to the right, it's going up forever, okay? So that's what that ending behavior is. Okay, the maximum number of turns has to do with the degree, right? So let's count the number of turns that it has, like how many times does it change direction, okay? And that's gonna happen at each of these local maxima and minima, okay? So it comes up, changes direction, so that would be a turn, right? And then it comes down, that'd be another turn, and then it goes up and it doesn't change direction after that. So it's gonna be 2. 2 is the maximum number of turns that this has, okay? Or that any cubic graph has. So it's always going to be 1 lower than whatever the degree or the highest exponent is. Okay, that's the number of turns. Okay, actual real zeros. That might seem like redundant that it says actual and real, but that's what, remember, we have imaginary numbers exist as well, and those sometimes those wouldn't show up on the graph. Okay, but what we want to look for, again, zeros is another name for x-intercepts. Okay. So what we want to look for is the places where this curve touches the x-axis. Okay, and that might require us in this case to zoom in a little bit because this one gets very close. Okay, but the places that this curve touches the x-axis, again, Desmos is nice and they highlight them for you. Okay, but we see right here -2, 0 and 1, 0. Anytime you have an x-intercept, the y value is going to be 0. So we have -2, 0, and 1, 0. Those are my 2 x-intercepts. Okay, so that's what I would list as my 2 zeros. And again, like those show up on the graph, so those would be the real zeros. If it was asking for all zeros potentially, then you might have to plug in 0 for y in the equation and solve, and then you might find some imaginary ones too. Okay, but that it's not asking for the imaginary ones, so we're not concerned with that. Okay, now relative max and min. Relative is another name for local. It says local here at first, and relative is just, I like the word relative actually better because that's it's more relative to where it is in its position. Okay, but so relative and local mean the same thing. So a relative max and min. Okay, again, max, you think maximum highest point, right? Minimum lowest point, right? So when it's the highest point on a curve, that would be a relative max. Okay, and so in this case, our max, again, you can have more than one of these, but just in this case, we just have one of each. -2, 0 would be a max, and then a min would be this 0, -4. Okay. Uh-oh. Excuse me. Okay, so there's our max and mins. And again, in this case, they just happen to be right on the axes too. They're not always 0 as one of the values. You can have maxes and mins anywhere. It just happens to be that for this problem. Okay. Now let me do domain and range real quick, and then I'll pull up an image of what the increasing and decreasing intervals looks like. Okay. So for the domain and range here, okay, the domain and range, again, we've talked about that before. But the domain, okay, the domain, again, we're wondering how far is this graph going to extend in terms of the x values, or to the left and to the right? And again, a better question might be, is there a limit to, is there a specific place where it stops expanding left or right? And no, there's not, right? It kind of, you see that if you focus on the x values, as I go down here, they continue to just gradually increase, right? -6.9, -7.3. They will continue to do that all the way down, okay? So this graph will never stop extending left and right, okay? The same thing as it goes up. So that we would say for that all real numbers, okay? And then for the range, same kind of question, except instead of thinking in terms of left and right for the x values, we're thinking up and down for the y values. So will this graph ever stop extending all the way down or all the way up? No, it will never stop, right? So the range here also is all real numbers. Okay. Okay, so that that's an easy one, right? It's not always all real numbers for both, but it is in this case. Okay. Now that nasty thing there with the all real numbers. Let me actually pull this up and we can look at it together once it starts loading here. Okay, shout out to Mr. Donatelli for these notes. These are actually his handwriting. So, you know, Mr. Donatelli, you can thank him for me. Okay, now let's look at this. Okay. So you see, he sketched the graphs on here, okay? And he did a great job. These are good looking graphs, okay? So in this case, okay, we see that, look what he did, okay? Each of these turning points, it's hard to see the letter B here, and that's a dotted line right on the axis there, but I can actually kind of mimic this on Desmos here, hold on. So just ignore what I have over here on the just ignore these. These have nothing to do with the equation. Okay, I just want you to more see the dotted lines. Okay. Okay. So look what he did. Each of these dotted lines, look where they are. They're on the turning points. They're on the x, specifically the x values of where your turning points are, right? The graph changes direction right at A here, so there's a dotted line there. And there's a change of direction right here, and there's a dotted line there. And that's what we're looking at when we're talking about increasing and decreasing intervals, because what's happening with the graph is it's changing directions at those specific spots. So what it's asking is, what are the intervals where the graph is increasing or going up, and what are the intervals where the graph is decreasing or going down? So a way that we can illustrate that is by kind of chunking the graph up using these dotted lines, right? And then giving those chunks of the graph a name, right? And so, like, you can see in the notes he called this dotted line letter A and this dotted line letter B, and that's what I like to do too. Okay. And so we can actually look down and see what he wrote for that. Okay, so for increasing intervals, that is 2 zoomed in. Okay, so for increasing intervals, okay, let's break this down. So he says, when x is less than a and when x is greater than b. Okay, so let's compare that to the graph. When the x values, so thinking left and right, when the x values are less than a, the graph is increasing. And that's true, right? You think the graph is going up, up, up all the way, right? It's forever, right? The y values are negative infinity. The x values are, as the x values go up too, it is increasing that whole time. Right? And it's easier to see that on Desmos, right? This entire time as you're going down, everything's increasing, 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 right? And then right here it changes. That's that turning point, okay? So that's what that means. When x is greater than a, or when x is less than a, excuse me, or lower than a, and x is lower than -2, so when x is -3, -4, the graph is increasing, okay? And so that's how we would say that, x is less than a. And then for decreasing, okay, because what happens there? It stops increasing and then it decreases for a little bit of a time, right? So this is kind of saying a is less than x, which is less than b. That's a fancy way of saying between letter A and letter B, the graph is decreasing, okay? And so that's a way that you can say that, okay? So between letters A and letter B, the graph is decreasing for that part. And then under increasing again, x is greater than b. So this second dotted line is b. The graph is increasing again, and then it always starts increasing again, just like it did at the beginning part. Okay, so that's really confusing for kids, and I know that. So I'm not sure, again, I might not be teaching your class for some of these things, but so if your new teacher has a better way of explaining it, then that is great, but this is how I like to say it. It's going to be tricky no matter how you think of it. But, so there you go. Those are some increasing and decreasing intervals for you there. Okay. Now looking at number 4, excuse me. Last one I'll do here. Same idea. Let's just go through and define each of these things, and then that'll be it. Okay. So I'll type in the equation y equals negative x to the 4th plus 2x cubed plus 4x squared minus 8. Okay, so we see this graph, and it goes all, it's crazy looking graph, right? This one's almost looking like a letter M, but that second little loop there's way higher. Okay. So in this case, when we talk about this shape, okay, when we talk about this shape is the first question, right? Normally 4th root graphs are in that like W type shape like this. Okay. But you might remember from transformations, when that A value or that beginning coefficient is -1, that vertically flips the whole graph. And so you see that W shape kind of flips upside down to look more like this. Okay, and that one specifically, right, the standard is for it to be like normal like that, but in this case, this graph loops higher like that. So this making me think of the SpongeBob, M for Minnie and W for Wumbo. You flip it around, right? So classic SpongeBob reference there. But okay, so anyway, we look at this graph, okay, and so we see, again, talking about the ending behavior. Again, as the graph extends to the left and to the right, what is happening? Well, for this graph, the graph is, again, starting low and going down low forever. So that would be down to -infinity, and to the right, is it going up forever or down forever as it goes to the right? It's going down still, right? It's decreasing. It loops up here for a time, and it's going down. So that also is going to go down to -infinity as it on the right of the graph, okay? All right, now the number of turns here, let's count them, okay? We have, let's zoom in a little bit. We have a turn here. It changes directions right here, very briefly, right? It's going up, 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 stops. It's going down for like the smallest bit of time, and then it starts going up again, up, 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 all the way up here, and then it stops, and then it's going down. Okay, so in this case, we would say the maximum number of turns is 3. Okay, 3 turns in this case, because again, it's always going to be one lower than the highest degree. Okay. All right, and then so the x-intercepts of this, okay, again, where does it cross the x-axis? We can see that on here, right? Just focusing on these two, 1.275 and 3.302. Okay. I totally forget what the decimal is. 032. Dang it. Okay. Clearly, I am in the school building here still. Okay, so then from here, those are the two x-intercepts, okay? Max and mins, okay? So in this is a problem that we're going to have more than one of these, okay? So again, max and mins, we're thinking on this graph, the highest and lowest points of each of these little dips, okay? So this one right here would be a max, right? That's a max point because that is the highest point on this little dip right here. So we'd say for a max, we would say this point, -8, 0.851. And, oh, I forgot my other value. But this is also a max up here, right? So I'll write that as a max as well, if I could get this to work. .351, 9.5. I'll just round some of these. 2.391, 9.548. Okay, and then the min, I forgot my other value. Thank you guys for being patient with me. These are the parts I would usually edit out if I was able to edit, but not on the school computer. Okay, And then this min point right here, this one min point, right, this bottom of the dip right here. Let me just zoom in to make sure. Yeah, that bottom of the dip right there, 0, -8. That would be the lowest point, as well as the y-intercept. Okay. Excuse me. Okay, so there's the max and mins right there. Okay. So there we go. Increasing and decreasing intervals. I'm going to show you Mr. Donatelli's because it's going to be annoying to draw in here. But then the domain and range. Okay, this is good to show on here. So domain and range. Okay. So again, domain. Will it ever stop extending left and right forever? And you can see as I very gradually go down and down and down, the graph just very slowly gets wider and wider and wider and wider, and it'll never stop expanding like that. So the domain is going to be all real numbers, or ARN. Okay. Then the range. The range is not all real numbers for this one, okay? Because if we ask, does it extend up and down forever? No, it doesn't, right? It's going to extend down forever, but it does not extend up forever, right? The highest point it ever touches is up here, okay? And so this y value is really important because that's going to tell me my number for my range, okay? So what I would say is for the range, y is less than or equal to 9.548. Okay, let me include my equal to. Okay, y is less than or equal to 9.548 because that is the highest point that the y value on the y-axis that it ever gets to. It never goes higher than that. It's going to go there, and it's going to touch all the y values below that. Okay. Then increasing and decreasing intervals. Again, so what you do is you put a line or a vertical line on each turning point. Okay. And so you see that this one's a little bit more involved because we have more turning points, right? We see what Mr. Donatelli did. A turning point, the first turning point is line A, the second turning point is line B, the third turning point is line C. Okay, so we have we actually have 4 different intervals to this graph. Each dotted line breaks up the graph into another chunk. Okay, so we have this chunk right here. And so we're wondering, okay, is that increasing or decreasing during that part? And it's increasing, right? And then between A and B, it is decreasing for a little bit. And then between B and C, it is increasing again. And then C, and then down forever, it's decreasing again. Okay, so you can see it's kind of alternating each time between each turning point. And this notation right here just kind of is another mathematical way of saying that. So it's increasing, X is less than A, so that's to the left of A. So forever to the left, all the way until line A, it's increasing, right? It's going up. And then between lines A and line B, it's decreasing. So that's how we write that. And then between line B and C, it's increasing again. So we write it there. And then from X, when X is greater than this C, right, it's going to it's decreasing forever. Okay, so that's how we'd write that. Again, I know the notation's difficult, but that's what we would say. Okay, guys? And I won't bother writing it over here because you just saw it. But okay, guys, so that is all for graphing polynomials, just learning some new terms and some new things here. Okay, thank you, guys, and that is all.